Hello, everyone, and welcome to today's Gifted World Masterclass. Today is Saturday, the 18th of July. I'm Siddharth. I am an ecologist, but nowadays I spend most of my time working in education. I work with an organization called GenWise. We nurture talented students, mostly in the middle school ages between age 10 to 14. Across India and the UAE, and even students from other countries all over the world. Our focus is on enrichment. We believe that there are so many beautiful things that you can learn about that incite curiosity, that make you ask more questions. And we believe that I really believe that students need to be brought into the world of questioning, into the world of curiosity, and not necessarily need to be brought so quickly into the world of answers. A lot of our schooling takes us straight to trying to find the answers. So in today's session, I hope that you leave with a lot of questions. Okay, so 430 is the amount of carbon dioxide in our atmosphere. Okay, that's 430 parts per million, which is a remarkably small amount. Okay, sorry, there's just something up with the annotator. I'm not sure why. Give me a minute. Okay, so yeah, sorry. So that comes to 0.043%. Can someone tell me what is the percentage of nitrogen in the atmosphere?
Sir, 70,
78, sir.
72, 71.
So roughly 71% is nitrogen. How much oxygen is there?
28, 27. 28 or 27.
Okay, 27%. So why are we all so hung up about this tiny quantity that is 0.043% of CO2? Right? How does something so small make such a difference? As an analogy, if you consider the stadium in which the FIFA World Cup is happening tomorrow, that stadium has 82,500 seats. That's a lot of seats. Okay. And if that was our atmosphere, only 36 seats would be carbon dioxide, which is minuscule. It's tiny. Right? So how this whole session started with me wanting to understand for myself, right? And then teach you guys. How does such a small quantity make such a difference? So here are the major constituents of our atmosphere: nitrogen, oxygen, water, and carbon dioxide. Okay. Can you tell me so let's leave water aside for now. What are differences that you notice between how nitrogen and oxygen are versus how carbon dioxide is? Krishiv?
Nitrogen and oxygen have the same element and they are diatomic, and carbon dioxide is triatomic.
Okay, so there's a difference in elements. Okay. Anyone else?
Sir, carbon dioxide is the only thing that has carbon in it.
It's the only one that has carbon in it. Okay. If we look at water, what differences do you notice between water and carbon dioxide?
So water is polar.
Water is polar. What do you mean by that?
A part of it is positive, the other part is negative.
Okay.
Another
So-
thing.
So one moment. This is an interesting thing that here it's negative and there it's positive. Let me just change the color. Maybe that will help. Oh, no, it's completely invisible. Okay. I figured out what the pointer issue is. Okay, cool. Someone was saying another thing. Go ahead.
Yeah, this polar, this polar property of water, it is what makes other substances dissolve easily in water.
Okay, cool. Sorry, just need to erase this mess that I made over here. Okay, excellent. So those are some interesting things that we will discuss. Eraser has done. Okay. So the other thing that just from here, if you don't know anything about polarity or these molecules, you can see that the water molecule is bent, whereas carbon dioxide is straight. It's a line, right? So that also figures in how things work, and we'll get to it, right? So, yeah, we should do things in order. This is a very famous graph. It has been used since the very early parts of discussion about climate change. So around 1990, when it started becoming a thing that people started being worried about climate change, they looked at this graph, which is the amount of carbon dioxide measured in the atmosphere at Mauna Loa Observatory. Sorry. Yeah. Okay. So this is an observation. Mauna Loa is an island in Hawaii. It's a mountain on an island in Hawaii. If you ever look at a globe, Hawaii is bang in the middle of the Pacific Ocean. It's really, really far away from big polluting industries. And therefore, it's a very good measure of what's happening in our atmosphere. And if you look at this graph, you can see it has been steadily increasing from about 300, 310 parts per million back in 1960 to 430, where it is now. 430 is the weekly average of the last week at this observatory, right? And we have really good data about this. There's one really interesting thing about this graph, and you can see that it kind of goes up and down, up and down, up and down, up and down. Any idea why? So it looks a little like a saw. Any ideas of why this saw is here? Okay,
Maybe due to climatic changes or weather change.
Weather changes, okay. So before we go to why it is there, let's first think about what exactly is this saw. Okay, so I'm just zooming into it. Okay. What do you notice about this pattern? The red line is weekly or monthly data, and the black line is an average. So that's why you can see the black line going relatively smoothly, whereas the red line is a more moment-to-moment data.
We can see that the black line cuts through this saw structure of the red line equally.
Right. So that's what averages tend to do. Right. You have sometimes that are above average, sometimes that are below average. Right. Inian?
So
Yeah.
what if like seasonal changes and it's something to do with summer, winter, maybe?
Can you look at the
all of
graph
this-
and does it look like it has something to do with summer and winter?
Like you told that it's like going up and down, and each of these is like yearly. So each year has two seasons. So maybe in one season, maybe harvesting season, it goes up and something like that.
So you observe that each year within the year it goes up and down, up and down, up and down. Right? But we can see that also the average is going up, that each year the high is higher than the previous high, the low is lower than the previous low. Right? Yeah. So this, some people call it an image of the earth breathing. Okay. That is nice words, but basically what is happening, oops, sorry, wrong place. Yeah. Basically what is happening is here when we are in summer at the peak of the of this cap, this is that summer? Yeah. So what's happening is in the northern hemisphere, when it is winter, which is the start of the year, okay, plants are not very active. And so they're not doing photosynthesis a lot, but they're still respiring. They're still putting out CO₂. All the animals are still respiring. So in winter, the amount of carbon dioxide climbs. Once summer starts, because most of the land of the earth is in the northern hemisphere, when summer starts in the northern hemisphere, this is when winter is starting in the southern hemisphere, in Australia and South America, right? The photosynthesis by plants draws it down until it reaches a peak at the end of summer. Then again, next winter, it starts building up again. So this is a really beautiful thing that you can see that the biosphere, the living world, is really having an effect on carbon dioxide levels at an annual level. Okay. Oh, sorry. No. Yeah. Apologies, I misdid my slides. So now here's a question. The question we wanted to look at was, how does such a tiny quantity, what we've called a thin blanket, control so much of the whole world? If you took all the carbon dioxide in the atmosphere and you brought it down to sea level, it would be a layer that is 3 meters thick. And our atmosphere goes up for kilometers, right? So it's really, really thin. Okay. And part of it comes from having to think about how does the earth work, basically, right? How does taking care of heat on the earth work? So where does heat come to the earth from?
From the sun.
From the sun. So we have sunlight coming in over here. Okay. And have you all felt that heat comes to the earth from the sun? Like, is it just something you learn in textbooks, or is it something that you sort of have experienced?
We have experienced.
How?
Heat when the sun is at top, or when it is overhead, and very less heat when it is not that much directly falling over us. So we
Yeah.
can feel it.
Definitely, right? So we all experience it. I remember, this reminds me of a particular moment when I was doing my PhD at the University of Minnesota in the US. Minnesota is a cold, cold place in winter. It goes to like -20, -30 degrees Celsius. And on a winter morning, when I was fully covered up in my jacket and stuff like that, the sun was bright and shining, and I could feel the heat of the sun on my face, while the rest of me was absolutely freezing. And I was like, this gives me new meaning to the line, the sun is the source of all heat and light on the earth, which is in all our primary textbooks. Okay. So excellent. The sun is a source of heat. It's putting heat into the earth. So that means the earth should be heating up, right?
Yes.
Sir, it heats up but also cools down when it's not facing the sun.
It cools down when it's not facing the sun. It cools down in equal amount?
Sir,
because
no, it doesn't.
It doesn't? Oh. Okay, so if it doesn't cool down in equal amount, so if say I'm in Bengaluru, every day Bengaluru gets heated up by the sun, and every night it doesn't cool down as much, what will happen day after day after day?
Sir, it'll start getting warmer,
Temperature
more
will
like global
increase.
warming.
So the remainder will start to like stack up till it like increases the temperature.
So has this been the case of all of Earth's history?
No.
No, sir.
Hamsalekha says no.
No, sir. Because like the ozone layer, like it's the Earth also deflects back some of the heat when it's
Oh,
received by ozone layer. Like it also like deflects some of the like radioactive and magnetic, and the magnetic field and ozone layer like take care of some of the radiation, which like decreases it.
okay,
But
so
then
there's some around, let's say there's an ozone layer here, and that reflects some heat. Okay. The rest of it comes to the earth. And how does it go out in the night? So Viraj said that in the night, when the part of the earth that's away from the sun, the heat goes out. How does heat go out?
Sir, I think the air which is hotter rises up and then stays higher while the colder air settles down because it is more dense.
Right. So what you're saying is in the atmosphere, we're having a bit of circulation, but that heat is still within the earth. The atmosphere counts as part of the earth. Otherwise, we'd all be very dead. So how is heat going out? And let me just check the chat.
Because the carbon dioxide is creating like a hole in the ozone layer.
Okay.
And
So
that
let's
would
leave ozone out of it right now, because as we saw, ozone is a really, really, really tiny fraction of the atmosphere. And I promise you, it doesn't have much to do with this side of things. So it's just our friends, nitrogen, oxygen, water, and carbon dioxide. Okay, I will. So warm air going up, cold air coming down, it's a part of it, but it's still keeping it within the atmosphere, right? We're not losing the heat, and we need to figure out how to lose heat. The answer is we lose heat the same way that we get it. We get it as light, which you can see, but we lose it. Go ahead, Viraj.
Sir, I remembered a class where my teacher taught me about greenhouse gases. So greenhouse gases, there's carbon dioxide, and there are others, but I don't remember them now. They absorb the heat, which then get heated higher.
So we're still not answering the question of how does heat leave the Earth system, right? Because if
Yeah, I think that greenhouse
radiation,
maintain heat.
yeah, they maintain heat, but so Samyak, I think, Samyak was going to the answer that I wanted, which is radiation. It comes into the Earth as light that we can see and also that we can't see, UV light and a bunch of other things. It leaves also as light. It's just light that is too large a wavelength that our eyes cannot see. How many of you have heard of infrared light? Raise hands. Yes, it does. Sorry, hold on. I by mistake tossed my presentation into the wrong place. Okay, excellent. Where were we? Apologies. There we go. Yeah. So electromagnetic radiation, which is light, is the same way that heat leaves the Earth as it comes in. And I really need to talk faster. Okay. So this is an image, and I'll just walk you through what's happening over here. Okay. The y-axis is amount of energy, and the x-axis is wavelengths of light. Okay. So 400, this region over here is the region we can see. And so know that the lower down the wavelength is, the higher the energy that light carries. But that is, each bit of light carries more energy. Totally, when you see the radiation that we receive on the Earth, it looks like this, right? Okay, that's that yellow one. If you are above the atmosphere, the radiation we receive from the sun looks like this. Okay, it peaks in the visible spectrum. Okay, and that's not a coincidence. Okay, right? Like more likely, we evolved to see the available light to us. Right? If we evolved to see light in this range, then the world wouldn't be very bright. We wouldn't get a lot of information from it. Right? And the red one is what we see of sunlight at sea level. And you can see that it looks very different from the yellow one. In part, that difference is entirely due to the atmosphere, because here is the yellow is without atmosphere and the red is with atmosphere. And in the atmosphere, you can see that this bunch of radiation is absorbed by water. This bunch of radiation is absorbed by water. This bunch of radiation is absorbed by water. And therefore, we don't see it on land. It's all caught in the atmosphere. Okay. So note that in all the charts I'm showing you today, there is a bunch more detail that maybe might not make sense to you. But here's the fun thing. Okay. What I showed you just now was just this part of the graph. Okay. And this is the radiation that comes into the Earth. If you extend the graph out, this side, the blue side, is the radiation that goes out of the Earth. And roughly the same amount of energy comes into the Earth and goes out of the Earth. But what goes out is infrared radiation that is a lot less energetic. Okay. Now, if we see, now the thing is that all light interacts with matter, and all matter interacts with light. But as we saw in this previous thing, there are some wavelengths of light that are more strongly absorbed by certain elements, by certain molecules, and others that are not. Right? So, for example, the things that make up our atmosphere do not strongly absorb visible light, but they really strongly absorb this region here around 1300, 1400 nanometers. Okay. So each kind of molecule absorbs light differently. And this is where carbon dioxide really makes a difference. Because if we look at the light emitted by the Earth, we see that carbon dioxide absorbs really well in that area, as does water vapor in the area of light emitted by the Earth. Okay. So what does this mean? Okay. If this is the world, this is the Earth, we have a thin blanket around us that results in incoming light. The atmosphere is mostly transparent to incoming light. It's like we look up and we see the sunlight as it is. Okay. But the Earth is also shining in the infrared. And if we were to put an eye out here, right, and look at the Earth, we would see that the atmosphere is opaque to infrared light, to the shining that the Earth does. And that's because of carbon dioxide. Okay, why so? It's a very interesting digression that I did not expect over here. As we said, nitrogen and oxygen are identical, right? There is no difference in charge inside it. Okay, but an electromagnetic wave is something that interacts with charges. So for a molecule to be able to absorb an electromagnetic wave, it needs to be able to have charge in some way, have some difference in charge, have what is called a dipole. Okay, so we're used to magnetic dipoles, that every magnet has a north and a south. In a chemical entity, a molecule, a dipole means that in a chemical entity, a dipole means that one side is positive and one side is negative. That happens naturally in water because the big oxygen is more negative, whereas the hydrogens are more positive. In carbon dioxide, if you look at it, it's actually symmetric. So there is no dipole because maybe the oxygen is more negative, but you see that both the negatives are pulling opposite each other. So it doesn't have a dipole as it is, but these bonds can bend a little. So instead of carbon dioxide just being a line of three atoms, it can sometimes very briefly bend. Okay, and I'm exaggerating this bend massively. And when it bends like this, you have the carbon that's slightly positive and the two oxygens that are slightly negative, such that you get a dipole over here. Okay. Now, the energy of this bending correctly matches a region of infrared that is emitted by the Earth. And that is why carbon dioxide is very good at absorbing infrared radiation, whereas oxygen and nitrogen are not. Water also absorbs infrared radiation in the same region in a different way. Okay? But so this is why water and carbon dioxide are two major absorbers of infrared radiation. So what happens there? The Earth is cooling down. It's releasing out infrared radiation, but that hits our thin blanket of carbon dioxide, and then that carbon dioxide molecule starts spinning more, starts bending more. It collides into other molecules and immediately transfers the energy to them. And that energy transfer is just heat, right? Molecules bumping around each other harder is heat. So, yeah. So carbon dioxide is very good at catching the heat that the Earth is radiating out and bringing it back in. So this slow increase over time is, because of that, this slow increase over time of carbon dioxide is leading to an increase in temperature. However, this was only a short time series. People have also gone into ice cores in Antarctica. Okay, so when ice is formed every year in winter, little bubbles of air get trapped in it. And by drilling really deep down, scientists have been able to examine the data of the past 800,000 years and measure the amount of carbon dioxide in the air over 800,000 years. And we know that it has roughly ranged between around 300 to about 160, 170 parts per million during that period. Okay. And this is where we are currently. It's a massive, big spike. But before this, I want to go back even earlier. Okay. So that was only 800,000 years. This graph is over millions of years. Okay. And it's a story of how has carbon dioxide amount changed over that time. Okay. Yeah. So over millions of years, there have been periods when the ice has come in. So these blue things show what is the highest latitude at which ice has been present. Right? 300 million years ago, there was an ice age. Right? That's what the movie is about. And even more Ice Age movie is about here, not about 300 million years ago. Right? So there have been different ice ages over time where ice has covered the Earth. Since we're talking about radiation in, radiation out, ice really reflects light very strongly. Right? You've all seen it. Or those of you who have seen snow and ice know that if you go into the mountains, you have to take sunglasses. Regular glasses don't cut it because the ice reflects almost 90% of its received light. Water reflects only about 4% of its received light. So that's a huge difference. 4 or less than 1% of received light is what water reflects. So when we're talking about this energy balance of the Earth, the more ice there is, the less the Earth warms up. And therefore, if you start with an Earth with just a little ice, that ice reflects heat such that more ice comes. Now there's more ice, it reflects more heat, and more ice comes, and more ice comes, and more ice comes until you get an ice age. But this same feedback loop works in reverse. If a little ice melts and you get water, suddenly go from 90% reflection to 4% reflection, and all that heat gets absorbed. And so more more ice will melt because that water becomes warm and it melts ice next to it. So, and the same process works in reverse as ice is melting into water. This feedback loop between ice and water means that a very small change in the system, okay, if you slightly cool the world, there will be more ice. More ice means more reflection, less heat in the system. That leads to more ice. So that feedback loop means that if you very slightly push the system, you can change between a very icy world and a not so icy world. And that change happens through carbon dioxide levels. This blue line is the carbon dioxide levels. And you can see that whenever there was a major ice age, the amount of carbon dioxide in the air was quite low. And to break an ice age, you need a rise in CO₂ again. Okay. The other thing that you see when you look over millions of years is look at this y-axis. Around here, carbon dioxide was 1,000 to 2,000 parts per million. And here we are making a big deal of being in around 400 parts per million. Sorry, 400 will be here. Right? We're making a big deal about being in 400. But if we look over the old record, it's been 1,000, it's been 2,000, it's been so huge. So why is 400 a problem? Okay. So I want to go even further back in time and tell you why carbon dioxide and greenhouse gases are important. They're not just villains. Okay. This is a story called The Faint Young Sun. Okay. This is where we are now. Now, our sun as a star is getting bigger and it's also getting brighter over time. Time measured in billions of years, right? 1 billion is a lot of zeros, okay? We are very much not even an eye blink. We are a minuscule microscopic second in comparison to this graph, right? So when the Earth was young, when life started on Earth about this period, right? You can see that the sun was a lot less brighter. Okay. And at that point of time, there was a lot of carbon dioxide, there was a lot of methane in the atmosphere. And that is what kept us warm enough to have liquid water, for life to evolve, for all those good things to happen, which happened in this period. So in this period, carbon dioxide and greenhouse gases were our heroes. They are what enabled us to live. Okay, and by us, I mean tiny bacteria in the ocean. Okay. Then another fun thing happened. Somewhere around this period, photosynthesis evolved. That is, bacteria got the ability to use sunlight, to capture the energy of sunlight and convert carbon dioxide into sugars, releasing oxygen as a waste product. Okay. Now, all of that oxygen that was produced by photosynthesis went into the atmosphere. And in the atmosphere, it converted methane, which is a very potent greenhouse gas, into carbon dioxide. Oxygen went from being less than 1% of the atmosphere to more than 10% of the atmosphere. And it removed a lot of greenhouse gases. That resulted in a big cooling of the Earth. Okay. So it's just how these consequences like stack up on each other. That the invention the evolutionary invention of photosynthesis resulted in removing greenhouse gases from the atmosphere that massively cooled the Earth. Then again, we had to wait some time for carbon dioxide to build up again for the Earth to warm up again. So the creation of photosynthesis led to an ice age, probably back to 2 billion years ago. We don't have good, like we don't have no way of getting data of what was happening 2 billion years ago. But people strongly suspect that the introduction of photosynthesis, it's called the Great Oxidation Event, because our world went from being a world with very little oxygen to a world with a lot of oxygen. It's strongly believed that the Great Oxidation Event led to an ice age. Okay, I promised I would pause, and I've taken half an hour to pause. I'd like to take a minute. I've talked about a bunch of things. I'd like you also to take a minute to say what are questions that you have? What are things that look new? What would you like to know more about while I drink water? Go ahead, Krishiv.
Sir, I just wanted to ask again. So you're saying that ice creates more ice in the future, and then it takes a lot of more carbon dioxide to take that ice out again. But where does that extra carbon dioxide really come from?
Excellent question. We will discuss it. Thank you. Anyone else? Go ahead, Aprameya.
Sir, during the ice age, when all the animals froze or many animals died, how did they produce more carbon dioxide to bring back the level of temperature?
Great. I like how you all are asking questions that are correctly about the next part of my presentation. Thank you. It's very affirming. I see someone has said something in the chat. Can the great oxidation event happen once again? If so, how can we make it happen? Sadly, no. That was an evolutionary. So, okay, I want to clarify one thing about timescales. The great oxidation event took millions of years. Okay. Just remember the axes in this graphs. This is the faint young sun story is billions of years. This glaciation and ice age thing is millions of years. So none of these stories are helping us. The only thing that's on our lifetime kind of scale is this Keeling curve of carbon dioxide shooting up. Okay. So when we're talking about these Earth system processes, we're on whole different timelines. Okay. Great. So what we've established in this first part was how does such a thin blanket make a difference to this huge, huge Earth system? Okay. We saw part of it is because of the way that matter interacts with light. Okay. And frankly, learning spectroscopy was a course that was forced on me in my first year of undergraduate. And I now believe it should be fundamentally taught to every science undergraduate, whether or not they do chemistry, because it's just so interesting how many things connect to how matter interacts with light. The fact that you can microwave things that contain water versus microwaving a biscuit does nothing is entirely because water absorbs microwaves. Okay, so in the exact same way that we're talking about carbon dioxide absorbing infrared and heating up the atmosphere as a result of it, the same way when you put water into your microwave, the water is able to absorb microwave radiation. But you put something dry that doesn't contain water, it doesn't absorb very well. In fact, we'll see that over here. UV visible infrared. We didn't have a microwave. Sorry, I don't have a spectrum that has microwave in it. Okay. So part of the way this thin blanket works is just about the way CO2 absorbs infrared, which is a consequence of its molecular structure. Okay. And another part of it is the way ice and the thing that we were talking to about ice is called the albedo. Albedo is how much of light gets reflected by something. So ice has a very high albedo, it reflects a lot of light, whereas water, dark things have very low albedo, they don't reflect a lot of light. So that ice albedo feedback that Krishiv was talking about is something that enables a very small quantity of carbon dioxide to use these, to push these feedback loops into situations where you get a lot of ice and a lot less ice. But what controls carbon dioxide on a big time scale? Now we know that burning fossil fuels is what is really causing a lot of global warming. It's releasing a lot of carbon dioxide. But if you look on the scale of millions of years, it's a completely different thing called the carbonate silicate cycle. Okay. Now again, there will be a lot of details on this slide that some of you might not be able to understand. That's fine. Just listen to the version that I'm explaining. Okay. So most of the rock that is on Earth is calcium silicate. It's either carbonates or silicates, which means it contains silica or it contains carbon. Now, rain is acidic because of carbon dioxide. For those of you who know about pH, the H should be capital, a neutral pH is 7, whereas rain has a pH of 5.6, which is acidic. That's because of the dissolved carbon dioxide. Now, carbon dioxide dissolved in rain comes and hits rocks. Okay, this is not the earth, this is a rough rock. Okay, and the acid in that rock dissolves the rock a bit, putting out calcium and carbonate ions. Now, these calcium and carbonate ions get carried to the sea, where there are marine organisms, right? Shellfish, lots of creatures in the ocean make their skeletons, microscopic creatures, they make their skeletons, their walls, out of calcium carbonate. Okay, which is just so, and they make calcium carbonate by taking carbon dioxide. They take carbon dioxide and they convert it into calcium carbonate. So when the rock was being weathered, carbon dioxide got dissolved in water and came in that water to the ocean. Now it sits in the ocean for a really long time, and a lot of marine organisms build their shells. And when they die, those shells go to the bottom of the ocean. Now, this is a shunt that takes carbon from the air, carbon dioxide from the air, takes it to the oceans and buries it. So that carbon is gone. Until the movement of the Earth's tectonic plates, which most of you know about, takes that carbonate rock and tosses it into the magma. And that magma comes out of volcanoes releasing carbon dioxide. Okay. So there have been ice ages on Earth where a lot of the world was covered with ice. Because a lot of the world was covered with ice, this weathering process that we saw, where rain falls on rock and that rock takes carbon dioxide into the ocean, that just can't happen, because when rain falls on ice, there's no carbonate to weather. Okay. And also, it doesn't really rain in Antarctica. You need like warm winds, you need humidity to rain, and it doesn't rain when there's ice. So when in those ice ages, which you can see in this graph over here, right? Some of these massive ice ages here. It took millions of years of volcanic eruptions releasing carbonate that was buried in the rock to build up atmospheric carbon dioxide enough that the blanket became thicker and then heated up the earth to remove the ice. So Krishiv and I'm sorry, I forgot the name of the other person who asked the question of how does carbon dioxide come back, right? Or how does it increase? How does it decrease? This is the Earth's thermostat on the scale of millions of years. Okay, and this is the thermostat that we're seeing at work over here. That when it was going down, it was because weathering of the rocks, rain was weathering the rocks and taking all the carbon dioxide to the ocean, and sea creatures were making their shells and burying it. And then in this whole period where there was lots of ice, all that carbon dioxide wasn't getting sucked in and it was getting emitted out by volcanoes. And so volcanoes brought it up until again it comes back down, right? So this calcium silicate shunt is a geological cycle. It happens on a huge scale. Okay. And that's the reason why carbon dioxide has been so high in the past. Now, commonly, these are core doubts about why is climate change really a thing? Have humans really caused it? Right? Because if carbon dioxide has been thousands of ppm in the past, right? Why is 400 a problem? The answer to that, apologies, my slides are a little all over the place. The answer to that we already saw over here, that all of these cycles happen very slowly. But you can see over here the speed at which we have done this has been so fast that the system doesn't have any way to adapt. The carbon silicate cycle that I showed is something that happens over millions of years. So if we wanted that to regulate our system, it can't when it's been pushed so hard, right? So, wait, yeah. Oh, this was the albedo part. Yeah. So this is the reason why carbon has changed over long periods of time. Now, here's an interesting thing. We say that we have added a lot of heat into the atmosphere, so much more carbon dioxide, it's making a thicker blanket, right? And so we're retaining so much more heat. 70% of all the excess heat generated since the Industrial Revolution has been captured in the ocean. As more carbon dioxide goes into the atmosphere, more of it dissolves in water. Okay. How many of you have heard of hemoglobin? I see only Krishav raising his hand. It's not a lot of raised hands. Okay. Why? So blood is red because of a pigment called hemoglobin. Red blood cells exist primarily to carry this thing called hemoglobin. And hemoglobin exists because oxygen really doesn't dissolve in water. Okay. So in order to get oxygen to all the parts of your body from your lungs, you need something in your blood that helps transport oxygen, and that's hemoglobin. Has anyone heard of like carboglobin or something to transport carbon dioxide? Okay, Krishiv is saying a yes. Krishiv, what is this? Is there something special for transporting carbon dioxide in the blood?
Sir, I'm not really sure about blood, but I guess there is something, some chemical I really don't remember, but I guess there was something that combines with carbon to make it more transportable in our body, I guess.
Okay. So uh, actually, you don't need anything special to transport carbon dioxide. It dissolves in water very well, which is precisely what we're seeing over here, right? The reason rain has a pH of 5.6 is that the carbon dioxide has dissolved in it. So in the human body and most all oxygen living creatures, right, they don't have to worry about transporting carbon dioxide out because carbon dioxide dissolves very well in the blood. Okay. Now, what is climate change doing? Or human-induced climate change, because of all the additional carbon dioxide we've been pumping into the atmosphere, that carbon dioxide is dissolving in the ocean. The ocean is becoming more acidic. And in an acidic ocean, it is difficult for sea creatures to do this, to build their shells. And because it's difficult for sea creatures to build their shells, we are slowly breaking this part of the cycle where calcium carbonate is not getting deposited as much on the ocean floor. So the rate of increase in carbon dioxide is also jeopardizing this part of the cycle. Okay, because if more more sea creatures build shells and more shells get deposited on the floor, that is something that is taking out carbon dioxide from the atmosphere and dumping it in rock, and it will stay there for millions of years. But we're not doing that. The other aspect is water that gets heated up. A lot of this carbon-rich water is going into these cold currents and cold masses of water that stay at the bottom of the ocean for hundreds of years. They're quite slow. But over time, that carbon-rich water will again come up and it will release all that carbon dioxide back into the atmosphere. So even if we were to completely reduce the amount of carbon dioxide we're emitting right now, we're already on track for there to be really high levels of carbon dioxide for the next 100, 200 years because of all of it that has been captured by the ocean. Okay, so we've discussed a lot about carbon dioxide, the special ways in which it absorbs radiation, how it emits, and we've seen how it's controlled over the scale of millennia, hundreds of thousands of years, by this rock weathering cycle. I have a random side story about the oceans. Right. So we're all very used to land, right? And we live on land, we see plants, we see trees, and we're like, oh, trees barks wood, there must be a lot of carbon over there. And we're used to the idea that you need a lot of plants for herbivores to eat them. And if there are these many herbivores, there are many fewer carnivores because only those many carnivores can live off these many herbivores, and these many herbivores need so much plant to be able to live. What is the bottom of the food chain in the ocean? Anyone?
Plants, the aquatic plants.
Okay, aquatic plants. So like when you look at a lake and you see water hyacinth everywhere, that kind of aprameya?
Sir, algae.
Algae.
Sir, it
Yeah.
has to be some primary fish food or something.
Uh-huh. Yeah. So it has to be something that is doing photosynthesis, right? And plankton. Yes. So plankton, they are called, I'll just put it. in the chat. Oops, they're called phytoplankton specifically. Okay, so plankton is a whole range of tiny things that live in the ocean. Phytoplankton specifically are the set of those tiny things that that do photosynthesis, hence the name phytoplankton. Okay, and the great oxidation event that I told you about 2.5 billion years ago, there was nothing living on land at that point of time. Everything just happened in the ocean. Okay, so we sort of feel over important because we're land creatures, but come on, 2/3 of the earth is ocean. Okay, and so all of these phytoplankton are there. Because they are microbes, they can grow really, really fast. And therefore, where on Earth we're used to these pyramids where there's a lot of plants and then less herbivores and then less carnivores. In the ocean, in some places, it's inverted because the primary producing layer is all microbes. They can grow really fast. And therefore, a small standing stock of microbes of phytoplankton can feed a larger standing stock of fish because they're growing so fast that the fish are eating only the new growth. Okay. That aside, there are several layers before you get to fish. There are other microscopic creatures that eat the phytoplankton and so on and so forth. But around somewhere in the last few decades, scientists studying the ocean discovered that viruses play a really, really important role in the carbon cycle of the ocean. Yes, thank you, Hansika. Zooplankton. Zooplankton are the non-green plankton, the ones that eat the phytoplankton. Okay. Viruses are really, really important in the ocean. If you pick up a sample of ocean water, there will be millions of phytoplankton, but there will be billions of viruses. Okay, and these viruses are killing ocean bacteria and killing phytoplankton, such that all of that action is happening near the surface. Okay, and because of the viruses killing them, they're falling down. Okay, but they're growing at a fast enough rate that at the surface they continue to divide and grow. Okay. Why is this killing important? How many of you have been to large lakes in India that are overtaken by water hyacinth? Right? It could even be city lakes. Right? This water hyacinth. How many of you have seen lakes that are overtaken by plants? Right?
In Ozar, there's one lake
Yeah. So you see
full
lots of
algae.
Yeah, so you see lots of city lakes, of urban lakes that are overtaken by plants. You see even rural lakes and large lakes like Chilika Lake, etc., or Vembanad Lake in Kerala, which has a lot of this water hyacinth growing. Okay, so the top layer of the ocean where light is coming can be extremely productive. But if you're overtaken with water hyacinth, you're not being productive. That plant is just sitting there and taking up the space. So these viruses, by killing phytoplankton, are making space for new growth at the surface where light can come and grow things. Okay, and all of that carbon is going down. And so it turns out that the fact that the ocean captures a lot of carbon through living things is in part because viruses are killing things. If you took the viruses out of there, which frankly you cannot do, those bacteria populations won't be dying so much and won't be sending all the carbon down. Okay. So I'll just come to the final part of my presentation that I want us to think about, and then we can wrap up with more questions if you have. Oh, I started the slideshow. And while I'm figuring out all this sharing business, feel free to think about what you have learned. Maybe note it down. I find taking notes very, very helpful for synthesizing what I've learned. Cool. So coming back to the idea of a thin blanket, okay, and how does something so tiny make a difference? Okay, it all has to do with stocks and flows. Okay, there is a lot of heat coming into the earth. There is a lot of heat going out of the earth every single day. Okay, photosynthesis, for example, captures only 1% of all the light that falls on it. Right? So 1% of the sun's heat energy that falls on a plant gets fully captured by photosynthesis. Yet on that 1%, our whole biosphere lives. Okay. So when we're talking about heat and heat exchange or energy exchange as heat, as radiated light, etc., between the sun and the earth, the flows are huge. Okay, which is why everyone's very excited about like solar power in space and stuff like that. Okay. But the stocks are relatively tiny. Right? How much is actually held back from that heat? So if we look at the earth and the sun, it's like these massive arrows of how much comes in, the massive arrow of how much goes out. Sorry, that was meant to be an arrow, right? And then there's a small amount that's cycling back and forth over here. And because you just need to because the amount in stock is very small, if you make a tiny change in the amount that is flowing, you massively change the stocks. So when we're talking about heat in the earth, the small change in the amount of carbon dioxide, the amount of greenhouse gases, slightly changes the amount of heat being released from the earth. That hugely changes the amount of heat present in the earth. Okay. There's a whole layer of black body radiation that is relevant for high school students and university students that we haven't covered today, but it was absolutely fascinating to learn while preparing for this, right? And we can go into that in the questions if that's required. So a small change in the in this flow makes a huge difference to the stock when we're talking about heat. But if we change our conversation where what we're tracking is greenhouse gases, okay, then the stocks of greenhouse gases in the atmosphere is huge. Just over the last, since that Mauna Loa curve I was showing, the amount of CO₂ being tracked since 1950, it's gone from 300, it's increased 1.5 times, right? The amount of carbon dioxide in our atmosphere, and more than that, the amount of carbon dioxide that is in soil and in the ocean is huge. Okay. With the Arctic melting, there are huge problems of permafrost thawing. Okay. So permafrost refers to the soil in areas that's not covered by ice, but soil that is permanently frozen. And permafrost carries lots and lots of organic carbon in it. And as the Arctic is warming and this permafrost is thawing, it's now because it was frozen, bacteria couldn't decompose all the living things that were there, all the living things in the soil. But now that it's thawed, it's no longer frozen, the bacteria are starting to decompose that, and they're releasing lots of carbon dioxide into the atmosphere. This is separate from the ocean situation I was talking to you about. The reason that because the stocks of carbon dioxide and greenhouse gases that are there in the earth and potentially releasable to the atmosphere, okay, are so huge, it is really, really, really important that we manage the flows. Okay. This is why climate activists, indigenous people, etc., are and so many people are saying that we need to stop using fossil fuels as soon as possible. We need to stop having deforestation because we need big changes in the flows in order to change these stocks. Big stocks need, in the case of greenhouse gases, we're in a situation where our small flow that is making a difference to the amount of carbon dioxide in there really needs to change now in order to keep these stocks at a manageable level. Okay. Stocks and flows are a very, very useful way of understanding all kinds of things, right? Whether you're talking about growth of COVID-19 disease, where the stock is the number of infected people and the flow is the new infection rate and people getting removed, people getting cured or recovering from infection. Whether it's talking about the economy, where like stocks is the amount of money people are investing, amount of money already there, and flows is the amount of money people are investing or taking out of the economy. Whether you're talking about your own health, right? This view of stocks and flows is something that comes under systems thinking more broadly, of a way of formalizing and talking about systems. And it's especially useful as an ecologist or someone who's looking at the world. I encourage you to think of more things in that way. And yeah. Excellent. So yes, that was my presentation for today. I hope all I'm curious to hear your reactions. I know we came talking about climate change. Maybe I approached climate change from a different way that you have. I'm genuinely concerned about what we do about it in the next couple of decades. But I'm curious to hear from you. What was something new that you learned? What was something unexpected? And what are questions that you're taking ahead? Feel free to write it in the chat, either personally to me or I'll call upon you who have raised hands. We can also do questions. Krishiv.
Sir, I wanted to ask, like I wrote it in the chat also. Sir, the calcium carbonate that gets deposited onto the ocean floor through the skulls of the organisms and the skeletons. So, like, is there like do they get converted to carbon dioxide or another materials over like millions or billions of years later, or do they just keep piling up?
It keeps piling up, and eventually plate tectonics takes that ocean floor into the magma, and that comes out in volcanism. So when we say that there's carbonate coming out through volcanism, it's because it's part of this cycle. That carbonate has gone from rock weathering, atmosphere and rock weathering into the ocean, and it comes out through volcanoes. So that's the only way out, volcanoes.
Okay, sir. Thank you.
Skanda?
Yes, sir. Sir, a new thing that I learned from this is that I didn't know that water reflects only 4% of light.
Let me get that water albedo figure correctly for you, but it's something tiny, basically. Okay, please don't take that figure entirely correct, but you can just search up the albedo of open ocean, ALBEDO of open ocean, and you can get that figure for yourself. It might be lower than 4%.
Yes, sir. Thank you, sir.
Thanks, Kanda. Vrishan?
Sir, I don't have a lesson, but I just want to give you my reaction after what I listened to today. I was like shocked. It was like I actually understand what the effects of carbon dioxide are. Like before, like in schools, they would teach us about what carbon dioxide is, but they wouldn't teach us how it works, what's the effects. They wouldn't teach us how. They would only teach us how and why it occurred. They wouldn't teach us anything like that. They would just explain the what and when. So now after like listening to this, now I really understand what's going on. And now I'm like basically shocked and concerned because like this trend of carbon dioxide has been increasing rapidly. Yeah.
Yeah.
So can I also leave? I have some
Yeah,
guests.
sure. Feel free to leave if you
Thank
want.
you, sir. Thank you so much, sir. Bye,
You're,
sir.
you're all here voluntarily, and I'm also here sort of voluntarily. So we can discuss whatever we want to discuss. Thank you, Rishan,
Yes,
for
sir.
that. I want to point out that especially at the middle school level, teaching a lot of this is extremely difficult. Explaining spectroscopy at a middle school level is not really something that you can easily go into or that would clearly convey fully, right, as a class in school. Maybe I think a lot more of us should work with school teachers to develop climate change appropriate material. Frankly, I did not expect to be talking to you about spectroscopy when I published this class a month ago, but it just happened. Maybe I like spectroscopy too much.
Hey, thank you, sir. Bye, sir. Have a
Thanks,
great day.
Nisha.